All right, so this video is going to be on alkyne addition reactions. These reactions are really similar to the addition reactions with alkenes, so we might be moving at a pretty good pace. But let's talk about the first one is hydrohalogenation. That's the addition of HX, and then we have halogenation, which is the addition of a halogen or two or more, and then hydration. So we've seen that as well, adding water. And then the last one is hydroboration and oxidation. Okay, so again, we saw these reactions for alkene additions as well. Now the example I'm giving you is a terminal alkyne, and that, remember, does have a hydrogen right there. That blue hydrogen is acidic. It sits on an sp hybridized carbon, and that actually has a 50% S character. So upon the addition of a base like sodium amide or sodium hydride, we can remove that proton to get this acetylide ion, and this is a good nucleophile, right? So early on, we did learn about how to use this as a nucleophile, but just as a quick reminder, on a super generic and lame alkyl halide, we will add that to chloroethane, and it's an SN2 reaction in this case, and we get, let's see if I can get my carbon count correct, 1, 2, 3, 4, and then we add a couple more carbons from that chloroethane. And that's all she wrote for that as a nucleophile. It's just important for you to remember that that's how you can make an acetylide to make even more carbon-carbon bonds, which is really all synthetic chemistry is. So let's talk about that hydrohalogenation. Okay, again, that's addition of HX across that carbon-carbon triple bond. And since there's two sets of pi bonds, then we can do it twice. Remember, if you have an acid, you want to protonate something. So that triple bond in red is the nucleophile, the blue H is the electrophile. And so we attack, and we get that chloride leaving, and that forms this new intermediate species where we have a vinyl cation. Okay, and so that blue hydrogen is there. The red bonds indicate that's where the electrons kind of came from for the original triple bond. You should also know that that positive carbon is sp hybridized still. So we have that chloride attacking the most susceptible spot, right? It's a good nucleophile attacking a good electrophile, and you get the vinyl halide now. Okay, we've seen this before because we know that this does not undergo SN2 reactions. But now let's say we have an additional HCl. Okay, well, we've already done this before, right? This is just an alkene now as far as we're concerned. We protonate that alkene. Now the question is, which carbon do we want to add the hydrogen to? Okay, well, remember, if we're going to add a hydrogen, then that means we're going to end up with a carbocation. You might think carbocation would be better on the carbon that doesn't have the halogen because it's electronegative, but that halogen being there actually helps stabilize via resonance, right? So let me move this down a little bit. And because it has a lone pair, right? So you can draw a resonance structure where that carbon does have an octet, so does the chlorine, but the positive charge is now on the chlorine, which traditionally we don't really like that idea, but it does create more stabilization because everything has an octet. Okay? So that chloride attacks that electrophilic carbon, which then allows that chlorine to be neutralized, and we get a dihalide product here. Okay, and remember, these chlorines are twinning, and so this is a geminal dihalide. So that's where you get the two red X's on that product in this chart, and that's hydrohalogenation. Okay. Just as a quick reminder again, this is a vinyl carbocation, not super stable like at all. So very reactive, doesn't really want to form. Not too ideal. It's sp hybridized carbon, right? And so this is actually less likely to form than so I say, sorry, not very slow, but a slower reaction than the HX addition to an alkene. So generally, we might see the alkynes being more reactive. They have more pi electrons and they're polarizable, but the formation of this vinylic cation is not ideal. It's not energetically favorable. And all right, so let's take a look at this internal alkyne, because it's going to look a little bit different. Now we're going to add 2 equivalents of HBr. Now we could have the addition of 1 equivalent, but if it's indicated 2 equivalents, then obviously we want to throw in 2. If it's not indicated at all, then we're probably having as an abundance of HBr, and we can assume there's at least 2. If it says 1 or 2 though, then you run with 1 or 2. Okay, so the final product is going to look like this. You should be able to just jump straight to this, but you should also know the mechanism that is required to get this product, right? Since there's 2 carbons that the bromine can add to on that alkyne, then you can get 2 different products. The previous one, you couldn't get 2 different products because one would require the formation of a primary or like a terminal vinylic cation, which is like hell no. So this vinylic cation right here gets the addition of the bromide to get the first species on the left, and then we can throw in another set of HBr, which would give us the final product. But again, on this one, being an internal alkyne, you might think like, okay, well, I can get a decently stable carbocation forming on the carbon on the right still, because it's again not bound to that electronegative bromine, and it's also not a primary carbon, right? So that's still not going to be the case, because again, bromine can donate its lone pair to stabilize that carbocation intermediate, and so you get this resonance stabilization here, and then you get the bromide attacking that carbon, neutralizing, getting to that final product on the left. Okay, now it's the same mechanism for the product on the right. Okay, so just remember that resonance stabilization is super important. Okay, and this is the product after 1 equivalent. Okay, so if we did write 1 equivalent, then this is the product that you would want to write. Okay, and there you go. So that, again, we've seen it's really analogous to the other the addition to alkenes, and so let's try this reaction right here. This is the halogenation reaction, and so what we're doing is adding elemental bromine. In this case, we could add elemental chlorine as well, but remember in the alkene addition we had that bromonium ion or the chloronium ion, so that's why we can't use iodine, because iodine's too big and it just really can't form that 3-membered ring, and so that's why it's only chlorine or bromine in this case. Okay, and remember the addition of those 2 bromines was anti-addition, which led to cis products, or I'm sorry, which led to trans products, right? So don't forget about that. That is basically the same case for the addition of a halogen to an alkyne. So after 1 equivalent, we get the trans dihalide. Okay, and after another addition of the halogen, we get essentially just a tetrahalide. Okay, so there's 4 bromines on there, and they're on neighboring carbons, and so that's a tetrahalide for 4 halogens. Okay, so the general mechanism isn't necessarily needed to be reproduced, but you should be aware of the fact that it's the same as alkene addition or alkene halogenation, and it results in trans products if you have 1 equivalent. Okay, so let's take a look at the hydration reaction. Now this one right here, this one's a doozy. It's kind of weird. There's a new concept called tautomerization, that you're going to need to understand, and I think that makes it more fun. Finally, something new, right? All right, so the idea of hydration is not a new concept, however. So we do know that we're essentially adding one water molecule to the alkyne, right? So whether it's terminal or internal, we'll actually get different results. Okay, so we'll see that. Let's take a look at the terminal first. Now, for terminal, we want to do water, sulfuric acid, and since it's terminal, we want to add the mercury sulfate. Okay, this is Hg2 plus. That's the mercury cation, and it's a Lewis acid catalyst. And this is necessary for the terminal alkynes because they're less reactive than the internal alkynes, just because of electron density. Okay, and what we're going to get is, if we count 1, 2, 3, 4, we're going to get a methyl ketone. So since it's a terminal alkyne, we get that methyl group on the right side, on the end. Okay, for the internal alkyne, we only need water and sulfuric acid, just like we only needed that for the alkene reactions. Now, in addition to that, we will get a different ketone. So it's not necessarily, it can be a methyl ketone, just depends. But we're not guaranteed a methyl ketone, whereas the terminal alkynes, we're guaranteed a methyl ketone. Okay? And that's just some of the subtle differences between the two alkynes, and we can better understand them if we do the mechanism. Okay, so let's try the mechanism. So it's terminal alkyne, so we need water, sulfuric acid, and our Lewis acid catalyst. Now the purpose of that is because it provides a 2 plus charged metal cation. And so anytime you have a metal cation, that's a Lewis acid, and it's going to help out for the most part. And we've got the pi electrons from the alkyne attacking that mercury cation. Okay, and so what that does is that kind of serves the purpose of like that proton, but it's better in this case with the mercury cation. And so we still get that vinylic cation intermediate, and what we end up doing is attacking that with the water, our nucleophile. Okay, and that product right here is going to be, as you might expect, the oxonium ion intermediate with that positively charged oxygen, which of course we want to neutralize. So we're going to go ahead and throw a base at it of some sort, in this case water, why not? And we remove that proton and neutralize it. So now what we end up with is something called an, it's an enol, but with a mercury cation on there. And this is obvious. This is going to be an intermediate species. Okay, we really need to get that mercury cation off before we proceed, and so the way we do that is just by the addition of that sulfuric acid. So that sulfuric acid is going to rip that mercury cation off. Sorry, I was jumping the gun. We're not doing the carbonyl yet. We're drawing the alcohol there with the alkene, and that mercury is replaced with the hydrogen. The mechanism we don't need to know, but that comes from the sulfuric acid. Once we have this enol, this is a reactive species. It really is an equilibrium. Just depends on the ketone or carbonyl group that you form, but it's going to move back and forth to. Excuse me, I forgot these the rest of the carbons here. My bad. It's going to move back and forth between that enol and that ketone. Okay, so this is the product, the methyl ketone. Let's take a look at the internal alkyne and see what we get. Okay, and we'll go over the that equilibrium between the enol and the ketone are formed. Okay, we'll go over the mechanism. So we still get the same process as before. Get that vinylic cation that is attacked by the water, remove the extra proton, we end up with an enol, right? And then that enol undergoes it's in equilibrium with the carbonyl species. Okay, and that process is called ketoenol tautomerization. And all right, so there we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's the same compound. I just drew it a little bit differently. And that's the ketone product. And that's the mechanism that you would write in order to get to that final product. But let's talk about those two equilibrium processes, right? Ketoenol tautomerization. What did he just say? What did he just say? Ketoenol tautomerization. Okay, so that ketone and that enol are tautomers. Tautomers. But let's see how that works. I'm going to give you a generic enol. Okay, so this is, it can actually go via an acid catalyzed kind of equilibrium or base, but in this case it's acid because we have that in the reaction mixture, and we're going to use the the electrons on the oxygen to create that carbonyl bond, that double bond, and kick out the pi bond to grab a proton, and then you remove that extra proton on the oxygen to get the ketone product. So it's really it's intuitive. I think once you see it, you should be able to reproduce it, as long as you kind of just remember you want to protonate things, right? And you want to protonate things in this case to get to the product that you desire. All right. Definitely, you probably have questions on that, so hit me up if you do. But that's the hydration reaction, and that ketoenol tautomerization is going to apply to both of them to give you what the methyl ketone as well as that regular ketone. So hydroboration and oxidation. All right. Let's try the terminal alkyne first. So remember that BH3 and the hydrogen peroxide and hydroxide was the way we did the hydroboration as well as oxidation. And what we ended up getting was an alcohol for the addition of alkenes, but in this case we're going to get an enol, which then tautomerizes to get you an aldehyde when you have a terminal alkyne. Okay, so let's go to the two possibilities. We have the approach of the BH3 like this or like this. Okay, now which one do you think it is? Remember, the boron and the hydrogen are the electrophile and the nucleophile respectively. Remember, the alkyne is electron abundant and electron rich, and can attack that electron deficient boron. So that's what we're going to do. And when we do that, we can almost think of that pi electron forming that vinylic cation like before, right? So we would want that vinylic cation to be on the internal bond rather than the terminal bond, because that's a more stable carbocation. But that's not really what happens. Remember, that hydride attacks that pseudo positive carbon in a concerted fashion. So it's a concerted addition of BH across that carbon-carbon triple bond to give you this this product right here with the one unit of BH3 added across that pi bond. Okay, and so they are going to be cis too, because remember, this is a concerted addition that was syn in the alkene reaction. And then after the oxidation process, we get an alcohol, and we just saw this is an enol, and enols can do tautomerization or undergo the ketoenol tautomerization, and that results in a carbon-oxygen double bond being replaced with that single bond, and the double bond, the carbon-carbon double bond, is now a single bond. And so in the presence of base, this is what we're going to do. We're going to remove that acidic proton on the oxygen, and then we're going to come down, we're going to create that carbon-oxygen double bond, and then that pi bond jumps out to grab a proton to get protonated. You could technically draw the carbanion first and then grab the proton, but this is how I would do it. And we get that aldehyde final product with the two hydrogens right there. Okay. Now, you can do this as a reverse. Remember, this is an equilibrium, so if you remove that acidic proton on the alpha carbon, you can create another pi bond that kicks the carbonyl pi bond up to grab a proton, and then that's how you go back and forth. Okay, and so that is the mechanism under basic conditions, okay, which is essential for this particular reaction since we already have a hydroxide in there. All right, so what's the difference between the terminal alkyne and the internal alkyne products? Well, let's take a look. We get the addition of BH3 across that triple bond, and we get 2 ketones, okay? So that's the difference. We really have the alkyne is super useful. The terminal alkyne is useful because we make that aldehyde final product, right? So that's for the terminal alkyne, we're going to get this aldehyde product. Notice for the hydration process, we got a ketone, right? So this just really depends on your synthetic goal. If you want to make a ketone, you go with the acid hydration, or if you want to get an aldehyde, you can go with the hydroboration oxidation process. And so that's why it's really useful to understand all of these reactions, so that way you can take different routes depending on what your end goal is. Okay, so let's take a look at this ketone and then work our way backwards to see where it came from in terms of like the enol, ketoenol. Okay, because then from there we could say like, okay, well, it could have been something else from there, right? But let's do it using the base. Okay, so let's remove this proton here. We create that carbon-carbon double bond, and then we create the negative charge on the oxygen. With both processes, we got the blue and the green arrows, so we're going to get 2 different products. Let's do the blue on the bottom. That creates the double bond on the left, and then a negative charge on the oxygen, right? And if we take that green approach, we're going to get the double bond on the right and the negative charge on the oxygen again. These species right here, they're not called enols because they don't have the proton on there. They're called enolates. Okay, so this is just more like, I did it this way to introduce this new like terminology to you. But after that, you could just protonate with water, right? So then you get your enol, your enol. Sorry, you should be able to move forward and backwards to determine what species you started with or how you got there. Okay, so again, that's just another reason why we did this one. But let's take a look at this guy right here. So what about which alkyne did this come from? Okay, so this one's, in my opinion, is a little bit easier because we need to have a carbon-carbon triple bond somewhere, right? And we can't really have a carbon-carbon triple bond with that ring. Okay, so that means that it has to be the 2 carbons that are not in the rings, and you can just jump straight to that. If you wanted, you could work your way backwards to form that ketoenol, or I'm sorry, I keep saying that, but you could just form the enol, right? And then decide what from there, after you rip off that unit of OH or H2O, then you can get the alkyne from there. Just working your way backwards on the mechanism. Let's take a look at this last one. Okay, so the reason why I want to do this is because the above alkyne can make that ketone with either one of those reagents, but this one is very specific and requires either the acid and water or the hydroboration and oxidation. So which one would it be? Well, it's either one in this case. But if we take a look at another scenario, what other alkyne can we form or use to create this ketone? And so if we threw, not that reagent, if we threw acid and water at this, as well as mercury sulfate at this terminal alkyne, you would also end up with that methyl ketone product, okay? And so that's kind of one of the things, like synthetic chemistry, there's lots of different ways to create the same product, and we should know these ways as far as we are concerned with the toolbox that we are aware of. If we used BH3 and H2O2 and a hydroxide on that terminal alkyne, of course we would get that aldehyde final product, which is not the ketone on the left. Okay, so I know this is a lot of stuff. I think really what you need to do is take the knowledge that you have and apply it to the practice problems, and then hit me up for questions. Okay, so you got this. Bye.